Hi guys, welcome back to the second data analysis video lecture. I'm Janine101014vid2 and today we'll start with a very brief overview of some concepts and data analysis resources available to us. Today I'll focus specifically on quantitative analysis. Remember, quantitative analysis involves the statistical analysis of numbers. In the fourth video lecture, we will focus a little bit more on qualitative analysis. So let's basically start with some concepts, okay? Mathematical operators and some symbols. It may all look a little like Greek now, but when we're done, it will soon be second nature to you. Also remember that there are certain mathematical operators we need to quickly get out of the way. First of all, two negatives make a positive. A negative number multiplied by a positive one makes a negative answer. And one more thing, remember BODMAS? This is an acronym for the order in which mathematical operations are performed. It stands for brackets of division, multiplication, addition, subtraction, and this is basically the order in which you should carry out operations within an equation. Mostly these operations are self-explanatory. Basically, we calculate things in brackets first, except for order, which actually refers to the power terms such as squares. Right, and remember I spoke in the previous lecture about there being different sources of data as well as different levels of measurement, okay? In terms of sources of data, we have primary and secondary data. We also have internal data, such as that type of data that you generate as a natural consequence of doing your job. For example, the number of days sick leave, clocking in and out, and so forth. External sources, on the other hand, include online sources of data, such as StatsSA or any other online databases, reports, and so forth. Essentially, these existing bodies of knowledge are considered secondary sources of data in that they're already in existence and you're merely tapping into them for the purposes of your study. Primary sources of data, on the other hand, is basically when the researcher themselves collects the data for the first time and specifically for the purposes of their study. It's always important to question the validity and the credibility with which data has been collected. And I can bet you now, most of you guys have sat in presentations and meetings and been presented with information and never even questioned the source, the mode of collection, or even the actual methods of analysis. This is a huge problem. Often decisions are informed by information that has been gathered. So if your information and data is faulty, what type of conclusions are you reaching? Remember I said that research is conducted with a specific purpose in mind. These purposes are often arrived at through observation of the world around us. We turn these casual observations into research objectives and aims, and we develop theories as to what we expect to see. This theory allows us to make a statement about the world around us. Theories allow us to make some sense of things and make decisions, and give us a degree of assumptions regarding what we expect to see given a particular event. In other words, we hypothesize, using a theory, what we expect to see. We test these hypotheses to determine whether our guess at the answer is true or if in fact we were just plain wrong. It is important to statistically test hypotheses, as very often our own judgment of what we think is true is clouded by that human thing called perception. Think about it this way. How many times have we had an argument with someone and we really could have sworn that we were right? Then there's that awkward moment when you realize, actually, you were wrong. We have two types of hypotheses, a null and alternate hypothesis. The null hypothesis assumes no difference, that the status quo remains, whereas the alternate hypothesis tests our theory. In other words, if we had a theory that work-related telephone calls increased our level of grumpiness, then our null hypothesis would assume that this theory is not true, and the alternate hypothesis would show that it was, in fact, true. In order for us to statistically test these hypotheses, we need what are known as indicators. Indicators require that we operationalize the construct. Wow, big words, huh? Let me break them down for you. When we test hypotheses, we need to identify our independent and our dependent variables. Independent variables are those things that we as researchers manipulate to bring about changes in our dependent variable or outcome variables. For example, if I look at the number of cups of coffee a person has and their level of alertness, the number of cups of coffee is the independent variable, as I, as the researcher, am changing or manipulating the numbers of cups of coffee, and then I'm measuring the level of alertness, or the dependent variable. But before I can identify the variables, I need to define what a variable is. You cannot test an hypothesis unless you define the variable in such a way that you can measure it. Turning a variable into a measurable construct is known as operationalization, and it is imperative that we do this before we set out to test our hypotheses. Often this is what people fail to do. They set out to test a correlation between, say, motivation and performance. Send out a questionnaire with multiple strongly agree, strongly disagree, like its types scale questions, which don't directly operationalize or measure motivation or even performance. How then do we correlate the two or test if there's any significant relationship? The answer is simple. We can't. So the first step, once we have decided on what hypothesis to test, is to come up with a measure that defines those variables. Then only can we test the relationship between them. Until then, it's just a guess. We hypothesize that motivation statistically impacts on output, but like I said, we don't know for sure until we measure it, and thereafter test it statistically. The second thing you need to bear cognizance of when deciding on particular statistical tests to employ in order to test those hypotheses and explore your data is the level of measurement at which a variable exists. This can range from essentially categorical variables where numbers merely represent words. For example, 1 is male, 2 is female, to actual numbers that can take on any possible number in the number line, from negative to positive infinity. For example, distance run. You could call your more categorical variables nominal and ordinal, and they're inherently discrete or whole numbers, whereas your more actual numbers are continuous, and they tend to exist at an interval and ratio level. You can do more mathematically and therefore statistically with the latter, as they are real numbers, whereas your nominal categorical variables have limited mathematical and therefore statistical application. If we use particular statistical tests on the wrong type of data, we will have erroneous outcomes. This indicates that certain tests performed on data have certain underlying assumptions that need to be met in order to produce valid and accurate outcomes. We can very often summarize the assumptions underlying parametric tests as follows. First of all, we have the assumption of normality. It is assumed that all the samples that you are analyzing have been drawn from populations that are normally distributed. You can get a rough idea if data is normally distributed by drawing a histogram of the data and examining the shape of the distribution. If the histogram has that normal bell shape, then it's probably normally distributed. Our second assumption is that of the homogeneity of variance. This basically indicates that your samples have variances that aren't highly different. If they are highly different, then it's difficult to get accurate results. This can be formally checked for, but is quite complex. We can cheat and say that if the two variances differ by a factor of less than 4, then the variance is probably homogeneous. This is a rule of thumb, so it's not perfect, but it seems to work a lot of the time. Lastly, we have the assumption of independence. This assumes that the sample and the means were calculated do not influence each other's scores in any way. For example, if you collect two data sets from the same group of people, as in the case of pre- and post-test designs, then these two data sets are not independent. So basically, these are the three general assumptions required for parametric tests such as ANOVA, t-tests, z-tests, and so forth. Parametric tests are also usually only run for interval and ratio levels of data. There are additional requirements for non-parametric tests such as the chi-square and Kruskal-Wallis and so forth, and these tests are usually more suited to nominal and ordinal levels of data, as these levels of data usually violate these assumptions. It is imperative that we carefully choose the right test that will yield accurate results. You don't want to be basing your decisions on inaccurate data. It could literally cost you. So far, we've covered some basic terminology and spoken through some of the factors you need to consider when choosing the right test, the right data, testing the right hypotheses, and coming to the right conclusions. There's just one more thing I'd like to include in this lecture, and that's the measure of quality for statistics. And these measures are validity and reliability. Validity basically refers to measuring what you said you are measuring. If you are intending to measure, let's say, motivation, you should ensure that your instrument is in fact measuring motivation and not say something like organizational culture, for example. The second term I referred to is reliability. This basically implies consistency. So, for example, if I were measuring weight and stood on the scale, and today I weighed 67 kgs, then tomorrow I stand on exactly the same scale and I weigh 69 kgs. This difference should be attributable to the fact that I've eaten the equivalent of 2 kgs of food, and not because the scale itself is faulty. Now, there are different ways in which we can establish validity and reliability, and in your dissertations, you'll need to clearly articulate how validity and reliability were achieved, not just state, what they are. Right, so that brings me to the end of this session. I'll continue with some more of the statistics in the third session, and then move on to the qualitative data analysis techniques in the fourth. All right, cheers for now.